my name is Cathal McCabe from the Xilinx University program, and welcome to the 5th XACC Tech Talk in our summer series. This series of talks is intended to highlight some of the research related to the Xilinx Adaptive Compute Clusters program. The program is a special initiative from Xilinx to support novel research in adaptive compute acceleration for high-end computing. XACC centers have been set up at partner universities around the world, consisting of compute nodes enabled with Xilinx Alveo compute acceleration hardware. Participants in the XACC program can access these nodes remotely for their research. If you are a researcher working in high-end compute and related fields, we invite you to apply to join the program, and you can find details on the webpage shown on the screen. To our talks for today, I'm very pleased to introduce Alberto Zeni from Politecnico di Milano, who will present his work on optimizing an implementation of the HPCG benchmark on reconfigurable hardware.
Hello, everyone. My name is Alberto Zeni, and I'm a first-year PhD student from Politecnico di Milano. And today I'm here to present you how we implemented the HPCG benchmark on one of the XACC clusters. So first of all, I will go through an overview of what we are going to discuss today. So first of all, I'm going through a historical overview of the HPC benchmark that are currently present in the state of the art and why we chose to implement HPCG on one of the clusters. Then I will go through how we implemented the HPCG benchmark on one FPGA, and then how we scaled up on multiple FPGAs, and finally discuss the results that we obtained and how we validated these results. So first of all, let's have a look through the HPC benchmarks that are currently present in the state of the art. So HPC benchmarks are used to evaluate and rank the supercomputers that multiple organizations are currently using. And mainly we have to consider three different benchmarks, which are the ones that are also the most well-known benchmarks. A Graph 500, which is a benchmark that relates to graph operations. The most well-known one is HPL, which stands for High Performance Impact Benchmark, which we'll go through later, and also HPCG, which stands for High Performance Conjugate Gradient Benchmark. So HPL and HPCG are the most relevant benchmarks for what concerns HPC systems, and HPCG is for what for us is the most relevant of the two, because it represents more closely a wide range of most commonly used applications. In particular, let's have a look through Graph 500. Graph 500 is a benchmark that has been introduced in 2010, and the goal of this benchmark is to promote the awareness of very complex data problems and graph analysis and graph explorations. Thus, it does not represent, it does not give the system a representation of what the system can actually achieve on multiple applications, but just focuses on a specific set that promotes graph exploration. Thus, is a very specific benchmark that does not correlate with most commonly used operations. While the HPL benchmark is the most well-known benchmark for HPC and is the most well-known benchmark. And this benchmark actually has been first released in 1979, so is the oldest of the three benchmarks that we are discussing today. What this benchmark actually does is compute and solve a system of equations that are very dense. So at the end, it actually computes dense linear algebra operations, which give the user or the one that designs the machine the peak performance of that particular system. So this benchmark is in fact very compute intensive, and it only produces and it only computes double precision operations with the intensity that we can see on this slide. So with HPL, though, there are many problems relating to the fact that this benchmark only performs dense operations. So first of all, most modern applications do not focus on dense linear algebra, and this makes the benchmark less relevant to what it was before. In fact, in the first year of HPL, when system manufacturers were looking to improve the performance of the system, they were looking to also, they were using HPL as a measure of what the system could actually achieve. The problem now is that because of the old concept of the benchmark, which computes only very dense very dense algebraic operations, is the fact that HPL no longer correlates with real-world applications, at least in the recent years. And moreover, HPC systems can also perform well in HPL, but differently in real-world usage. For example, there are multiple machines that are in the top 500 chart that perform very well in HPL, but worse in HPCG, or vice versa. There are systems that perform very well in real-world usage, but that do not perform, do not have the same peak performance as other systems in the top 500 base. So because of this, we come in 2015, a new metric has been introduced, and this metric is the HPCG benchmark. The HPCG benchmark, HPCG stands for High Performance Conjugate Gradient, and is a benchmark that has been implemented in a way to complement HPL rather than substitute it. So it is designed to closely match a different set of applications and still performs only double precision operations that like HPL, but is very important for the HPC system community, as it is filling the gap that was left by HPL when system manufacturers had in fact to look to improve the performance of the system. They might look at HPCG rather than HPL for most commonly used applications. What HPCG does is in fact solve a system of partial differential equations, and in order to do so, it implements multiple kernels that imply sparse matrix vector operations, sparse matrix vector multiplications, vector updates, global dot products, and also symmetric Gauss-Seidel smoothers. The challenge with implementing this particular benchmark on FPGA is the fact that we have to exploit all the possible memory banks on the FPGAs, as in fact, while HPL is a very compute-intensive benchmark, HPCG covers the opposite side, so it is a very memory-intensive benchmark. So in this case, in order to exploit the best performance, we have to first of all implement multiple compute units on the FPGA, and in order to do so, and in order to also exploit all of the possible memory bandwidth on an FPGA, we have to map efficiently all the memory banks on an FPGA to all the compute units available, which is not a particularly trivial operation. We also have to avoid as much as possible PCIe communication between the host machine and the FPGA in order to avoid losing bandwidth in order to communicate with the board. And finally, as I already said, we have to execute multiple compute units in parallel, changing a little bit the operation on the software side in order to implement OpenCL APIs that will exploit the multiple compute units implemented on the FPGA. So the first kernel that we implemented on the FPGA is the vector.product kernel. this represents a fundamental algebraic operation, which I think all of us already know. The vector dot product is in fact the product of the magnitudes of two vectors and the cosine of the angle between the two vectors. And at the end, what it is the sum of the products of the corresponding entries of the two sequences of numbers if the vectors are represented as vectors, as matrices of a single dimension. So in order to implement the vector product in the best possible way, we are implementing it using two HPM banks, one for each of the two vectors. And we are implementing the computation of the multiplication using with a pipeline, using pipeline, and also using packets of 512 bits. So no clock cycle is actually wasted on reading the results. We are directly reading the input and multiply and computing the results while we are reading the two vectors. We also implement a circular buffer in order to avoid resource contention between the final results and hide some of the operations. In fact, on the FPGA, floating point operations require multiple clock cycle. Thus, in order to hide the computation of the multiplication of the two vectors, we have to rely on a circular buffer in order to hide some of the steps required for the floating point operations. And finally, and also we exploit multiple HBM memory banks by implementing multiple compute units on the Alveo U280, which is our target board. And each of the compute units also processes part of the vectors. And then finally, we sum all of the results together in order to obtain the final result. The next kernel is the WAX beta Y kernel, which is a very simple kernel. And what the kernel actually does is basically add some two vectors, but also while adding the two vectors, it multiplies each of the element of the two vectors by a constant that is either alpha or beta. And this is done in order to, the object of this kernel is actually to stress the memory bandwidth of the system. But in order to implement it is a very simple benchmark, very simple kernel. In fact, what we did was implement a similar configuration to what we did to implement the dot product kernel without though the circular buffer. In fact, in this case, the circular buffer is not needed, but we need two axilites in order to implement to obtain the alpha and beta elements from the host side. And again, we are reading the inputs through HBM, and we are reading them using 512 bits packets. We are wasting again no clock cycle because we are reading and computing the inputs at the same time. And again, we implemented multiple compute units in order to both parallelize the execution and also exploit the most of the available memory bandwidth on the Alveo U280. So now we come to the SPMV kernel, which is one of the most complex kernels inside of the benchmark. And the SPMV kernel is a fundamental algebraic operation, of course, and it represents the product of the vector per sparse matrix. And the problem with this kernel is the fact that the input matrix is sparse, while the input vector and the output vector are actually dense. So the process of exploring the sparse matrix in order to choose which elements to multiply is actually a very difficult process to do on the FPGA. And in order to solve this, we actually implement a sort of hybrid of the compressed sparse row format. In fact, the compressed sparse row really stores, in order to implement our version of this, we first studied how the compressed sparse row format works. So this compressed sparse row basically saves up all of the non-zero variables on the matrix on a single vector, and then saves another vector that saves the start of these of the elements per row on the one-dimensional vector, in order to then be used to multiply the elements with the of course the dense vector. In order to avoid saving two vectors that will potentially increase the complexity of our kernel when implemented of the FPGA, we exploited one characteristic of the HPCG benchmark, which is the fact that each row has at most 27 non-zero elements when considered. So, exploiting this fact, we were able to basically flatten the matrix in such a way that all of the elements of one row were expressed via at most 27, but in order to which we simplified on 32 element vector. By doing this, we don't need a second index to navigate the first. We don't need a second vector to navigate the first vector, because we know that all of the rows of the matrix are represented on one single vector, and each row is long only 32 elements. So by doing this, we have a single dimensional matrix that can be sent to the FPGA basically linearly and can be explored in a linear fashion. Also, in order to do so, we have to pre-compute this matrix on the CPU side, and the effort to do so is actually accounted at the end in the results of the benchmark. But by doing this, the performance that we actually gain is much more relevant than the one that we could lose if we would explore the sparse matrix normally by splitting it up in multiple memory banks and potentially having multiple expensive memory accesses on the memory of the FPGA. So at the end, what we end up is this. It is a data structure that is represented by we obtain a matrix that is actually flattened, and that can be easily multiplied with the dense vector. And this is, of course, this implementation, of course, wastes some of the space, as we don't. First of all, we approximate the fact that we have 32 elements on each row, while we actually have at most 27. But also, when by saying that we have at most 27, we don't know if those 27 elements are always dense, as we have to imply the fact that they are, but we are actually wasting a little bit of space there. But what this actually enables us to do is the fact that we can actually parallelize the computation of the vector matrix product, which is very good trade-off for performance in this particular use case. So at the end, what we obtain is an implementation that again exploits the HBM of the Alveo U280 at most, and the computation is actually again performed in pipeline using packets of 512 bits. While reading, and we are also computing them. We have to, in order to do so, we have to again have a flattened matrix and a corresponding flattened vector that is replicated in such a way that the multiplication of the vector and the matrix can be computed in a linear fashion. And by doing this, we are also able to divide the problem in sub-problems that can be executed on multiple compute units, and thus we can implement multiple compute units on the Alveo U280 and exploit better parallelism again. And finally, we exploit by using multiple compute units. We exploit also multiple memory banks on the Alveo U280, thus exploiting a better memory bandwidth at the end. So the final vector, the final kernel implemented in HPCG is the symmetric Gaussian smoother. And what the symmetric Gaussian smoother does is actually a form of sparse triangular solver, which basically updates the element of a vector with the element of the sparse matrix that we were considering in the step before. And what this does is the operation that we can see on screen, which basically computes, which basically multiplies each element of the dense vector on the left by each element that is non-sparse on the right, and then updates the first element of the vector and so on. So what it does is basically pass through the vector and update all of these elements from top to bottom, and then repeat the process from bottom to top, which is and this actually represents the most difficult kernel to implement, represented the most difficult kernel to implement on the HPCG benchmark while we were doing the implementation. So in this case, we exploit a similar implementation to what we did on the sparse matrix multiplication that we implemented before. First of all, we have again the flattened matrix and the flattened vector saved on HPM, but we exploit again an optimization that we were actually able to achieve by implementing our hybrid format, which was the fact that we could store and leave the flattened matrix on the FPGA all the time. Thus, we didn't need to every time store it back, send it back to the host machine and then reflatten it. We store the flattened matrix on the FPGA all the time. And then we can exploit the fact that while we are updating the vector on the first pass, we are reading it through HBM. We can store it when we updated it the first time on the board itself rather than on chip memory. And by doing so, we are able to parallelize the process of actually updating the vector on the backward pass even more, as we are able to parallelize the computation of each element of parallelize the computation of each update of the vector in a much faster way, having access to much faster memory on the FPGA side. So finally, we have here we have an overview of what we actually implemented or what we did in order to actually implement the HPCG benchmark on FPGA. We first of all focused on sharing resources and storing data on the HPM as much as possible, and never delete the part that can actually be left there in order to increase data reuse. We also implement multiple compute units on every kernel and focus on executing the entire benchmark on board, thus removing as much as possible the PCIe bottleneck. Here we have an overview of the benchmark and how it worked. So all the kernels are contained inside a conjugate gradient block, which is called CG. Inside the CG block, all the kernels are stored in various order depending on the execution of the benchmark. And every time the CG block has finished to execute, we retrieve the result in order to check if the result is finished. Otherwise, we continue on executing. Here we have an overview of the resource utilization on the Alveo U280. We use most of the available resources on the FPGA, and we achieve actually 450 megahertz frequency. The bottlenecks in this case are the actual number of the high bandwidth memory banks, and also the DSPs. The DSPs, so the reason why we are using so much DSPs is because all of the operations inside of the benchmark are actually double precision operations. So this actually stresses this particular element of the FPGA because it has to compute multiple operations using that double precision operation, using double precision, and also it has to compute all of these operations mostly in parallel. Also, we are using a lot of LUTs because, again, if the DSPs are not enough, some operations are actually implemented using LUTs. And after that, we are using a lot of DRAM and UltraRAM. The reason for this is we are using a lot of URAM and DRAM to cache results while we are executing after we execute the first part of one of the kernels. For example, on the SYMGS kernel, which is the smoother kernel, we have to store the first pass of the update of the vector update on the board itself, and because of this, we need a lot of space in order to save this stuff, and then and because of this, we occupy a lot of memory on the FPGA itself. Moreover, we have to consider that in order to achieve the fact that we compute the benchmark on the FPGA, and we also want to avoid reprogramming the FPGA on the fly, because this will cost us significant time when running the benchmark, we have to implement all of the kernels inside of a single bit stream, and thus we are utilizing a lot of resources on the FPGA because we have all of these kernels combined on the fly. Moreover, having explored how we implemented HPCG on a single board, we also have to look on how we implemented HPCG on multiple FPGAs in order to improve the performance of the benchmark. So we implemented the HPCG benchmark using MPI. MPI is the message passing interface implemented inside of also on the original software version of the benchmark, and it is a standardized method for portable and for message passing for parallel programming. And it is in the original software, the problem of computing HPCG is divided within MPI processes, and MPI is used to sync the partial results of each MPI process every time one kernel has finished its execution. And because of this, the kernel can be actually parallelized using MPI. But the problem is that, at least for the software version, and as we will also see on our implementation, this introduces a little bit of overhead, having to pass data through multiple machines at once, but also passing, we have to pass, remember, to PCIe, which causes us a little bit of performance loss. In fact, as we can see here, these are the operations that HPCG actually performs, and HPCG uses send and receive operations in MPI in order to perform the halo exchange. So every time the SPMB kernel has finished executing, has to pass and sync up all of the parts of the computed vector with all of the other nodes, all of the other HPC and MPI processes, and also it has to use MPI or reduce in order to compute the sum of the final dot product operation after each kernel has been finished executing. So, in order to implement our multiple FPGA implementation, we had to again focus on avoiding PCIe communication as much as possible, and sync MPI and sync using MPI only when necessary between all of the various nodes on the XACC cluster. And we have to divide the computation evenly on the available FPGAs using a load balancer in order to avoid unbalancing the FPGA and resulting in an FPGA running for much longer with respect to the others. So what we did was actually reducing the communication between processes that were not necessary for the final computation. In fact, most of the overhead that is introduced in the original version of HPCG is due to the fact that each of the threads inside of a node of the MPI processes inside of the whole system has to sync up with all of the others. So we had to focus on the fact that most of the parallelization of the HPCG benchmark is happening within the same board. So we can think of an FPGA as one single core, and then we handle the parallelization inside of that FPGA, and then sync up only the results after the specific kernels that require synchronization, which are, as we already saw, SPMV and the dot product kernels. So finally, we evaluated our implementation using the HPCG original software, using the official release of the benchmark, the 3.1 release of the benchmark, and also against our FPGA implementation integrated in the same version of the benchmark. We used, said, the ETH XACC CPU nodes in order to test the CPU version, and the FPGA running on those nodes which were using Xilinx Alveo U280. As we can see here, the obtained performance of our implementation is around 100 gigaflops when using a single FPGA, and with regards to different, and this is considering multiple sizes of the benchmark, which are also used in other comparisons in the state of the art. And we can observe that our how our implementation actually performs when using 4 Alveo U280s, which exploits, which achieves around 330 gigaflops per second when running on 4 FPGAs, again, because of the fact that we have to sync up and we have the bottleneck of PCI Express when running multiple boards. And this is a performance comparison between our implementation and the implementation in the state of the art with different architectures and different technologies. And as you can observe here, we achieve similar performance with respect to the NVIDIA Tesla P100, which has a similar technology node to the Xilinx Alveo U280, which is a manufacturing process of around 14 nanometers. But most importantly, we achieve a significant performance improvement with respect to all the other architectures in terms of gigaflops per watt. Here we can observe how we, by cutting the synchronization between the MPI processes, we achieve an improvement of around 60% with respect to the original MPI synchronization on the benchmark. And finally, we also implemented the benchmark on multiple data precisions in order to observe how this would scale up with respect to the fact that we are using reconfigurable architectures. And as we can observe, we actually achieve double performance every time we have the precision of our benchmark. And finally, we evaluated the performance of our implementation using a roofline model. And we observed that our implementation is actually capped by the fact that we have limited memory bandwidth on the FPGA. And in order to avoid this, we would actually need a bandwidth that is around 1.8 terabytes per second, which is actually four times the current memory bandwidth. So in conclusions, as we observed, we achieved up to a 353x speed up with respect to multi-threaded HPCG when running on 4 FPGAs, up to 203x improvement in power consumption with respect to the same implementation, and an improvement in power consumption when compared to the benchmark running on NVIDIA V100, and 1.08 speed up with respect to the benchmark running on the P100 GPU. So thank you for your attention. I'm really sorry that I talked a little bit too much, but if you have any questions, I'll be answering them in the chat right now. And I leave the screen to Han Chen. Thank you.
Thank you very much, Alberto. The second speaker is Han-Chen Yi from UIUC, who will present ScaleHLS, so scalable high-level synthesis through MLIR.
Thanks for the introduction. And my name is Han-Chen Yi, and I'm a PhD student from UIUC. So today I will introduce ScaleHLS, a scalable high-level synthesis framework on top of MLIR. And I will first provide the motivations and background of the project, and then I will delve into the ScaleHLS framework and some optimizations included in ScaleHLS. And then I will introduce the design space exploration in ScaleHLS. Finally, before we conclude this presentation, I will provide some evaluation results. So first, in case some audiences are not familiar with high-level synthesis or HLS, basically, HLS is a compilation pipeline from high-level description of the program, for example, in C or C++, to RTL designs, for example, in Verilog. And there are several main stages in the compilation pipeline of HLS, including scheduling, allocation, and resource binding. And a lot of studies have shown that high-level synthesis can significantly reduce design complexity, improve design productivity, and identify performance area trade-offs for designers earlier. But meanwhile, design HLS accelerator is still challenging. So here is a very interesting experiment. Basically, a group of students are required to accelerate a certain model using CPU, GPU, and FPGA. And for FPGA summations, they are required to use HLS. And this figure shows the percentage of student submissions in each performance range. You can observe, so here the performances are normalized to 75% of expert designers' performance. And you can observe most FPGA summations fall into the range of 0 to 0.2. That means somehow high-level synthesis is more friendly to expert. And meanwhile, for large-scale HLS designs, that brings a large design space. And meanwhile, because there are some correlations between different design choices in high-level synthesis, making it difficult for humans to discover these complicated correlations. So facing all of these challenges, let's first look back at the question and ask question, like, how do we do HLS designs in practice? So here is a C snippet, which is a GEMM kernel. And when we try to apply this, map this program into HLS design, typically we will first do some directive optimizations and apply some HLS specific directives to optimize the quality of result. In this case, we're applying an HLS pipeline directive to the innermost loop level to improve the throughput of the nested loop. And the optimized design can be passed to external, HLS tools like Vivado or Vitis HLS to generate RTL code. But in most cases, just the directive optimization is not enough. We also need to do some loop optimizations to further improve the quality of result. In this case, we are interchanging the innermost K loop to the outermost loop level to achieve a better II of the pipeline. And meanwhile, we moved this statement. Let me open my laser. Okay. And we are moving this instruction in between the J loop and K loop into the innermost loop level to make the loop perfect and further improve the quality of result. So this is the loop and directive optimizations. However, in real HLS designs, we are not only handling one loop or one subfunction. we're having tens or hundreds of loops and subfunctions. So we can consider each loop or subfunction as a node in the computation graph. And they have dependencies, and there are dependencies between the computation nodes. And on top of this higher level computation graph, we also want to do some optimizations. For example, in this case, maybe we want to fuse the conv node and sample node into one node and map it to an existing IP. And with the graph with 3 computation nodes, we want to make them work in parallel. So basically, at the graph level, we want to do some graph optimizations like loop fusion, IP integration, and task level pipeline, and extra. So for now, people need to do manual code writing to apply the graph optimizations, and also loop optimization and directive optimization. So the difficulty of such an approach is the productivity is not that high, and also manual code writing is error-prone, making it very hard to enable automated design space exploration across all of these different optimization levels. So if we look at the optimization patterns of high-level sensor designs, we'll find actually this optimization problems can be better solved at different abstraction level, right? Like node fusion and IP integration and task level pipeline can be better solved at graph level. And when we lower the graph level representation to loop level, we can do all of those traditional loop optimizations. So this optimization pattern perfectly fit into the scope of emerging compilation framework called MLIR, standing for multi-level intermediate representation. So ScaleHLS is trying to exploit the MLIR framework to solve all of these HLS optimization problems at the correct abstraction level and automate them. So to achieve this goal, first, we need to represent the HLS designs at multiple levels. And then we want to make the multi-level optimizations automated and parameterized. And on top of the multi-level representation and optimization, we can enable an automated design space exploration. And finally, we also hope to have an end-to-end high-level analysis and optimization flow. So here is a brief introduction to MLIR. So basically, MLIR is a modular and extensible compilation framework, which is general to many domains. So in MLIR, it enables the users to define a C++ namespace called a dialect to customize their own operation types and attributes, making user be able to abstract their program at different level and optimize them and convert the program between different abstractions. So then let's take a look at the ScaleHLS framework. The input of ScaleHLS, we are supporting some high-level programming frameworks like Onyx and PyTorch. And these programs are first parsed into the graph level IR of ScaleHLS. We are using the Onyx and A10 dialect to represent the graph level IR. Here is a very simple example, which is a gem operation in Onyx dialect. So you can say it's basically a tensor operation, taking tensor types as operands and produce the tensor type as a result. And this graph level IR tensor operations can be lowered to our loop level IR. So in ScaleHLS, we are using a FAM and FAF dialect to represent the loop level IR. You can observe a very structured loop representation, similar to what we will write in a C program. And so this snippet shows the gem kernel lowered from this onyx.gem operation. And finally, to enable the HL-specific directive optimization, we introduce an HLCPP dialect to represent those HL-specific directives and structures. In this case, we are representing the pipeline directive using an MLIR as an MLIR attribute. So with this graph, loop, and directive level optimization, we develop a set of optimization passes for each of them, right, to solve the optimization problems we mentioned before at the correct abstraction level, including the graph, loop, and directive, right? And also to understand the the performance and resource utilization of the HLS design, or we can also call it the cost model, right, in a compiler. And we develop a quality of result estimator to estimate the latency and resource utilization through IR analysis. And we also package these optimization passes and quality of result estimator to transform and analysis library. So basically, this turns all of those manual code writing to callable and tunable interfaces, making it a perfect playground for design space exploration. And naturally, we also provide our own automated DSC engine to find the Pareto frontier of the throughput and error trade-off design space. Finally, we also developed an HLC frontend to parse HLC program into the MLIR framework, and also an HLC emitter backend to emit the synthesizable HLC code and pass them to the downstream HLS tools like Vivado or VITES HLS. Then I will go through some optimizations in ScaleHLS. The first group of optimizations is the graph level optimization. We have two passes, legalized data flow and split function. So here is an example with 5 computation nodes. So basically the goal is to make this computation nodes work in parallel. So when we apply the coarse-grained pipelining to this graph, it is also called data flow pragma in Vivado HoloSenses, we'll find that most of the downstream tools will not allow bypass paths like this to go through different pipeline stages. So we must organize the procedural 1, 2, and 3 into the same pipeline stage to meet the requirement of the downstream HLS tools. Provide us a coarse-grained pipeline with an interval of 3T. So here we are assuming basically every procedure have a latency of 1T. But then we find actually we can optimize this pipeline to a more fine-grained pipeline by inserting copy node and ping-pong buffers to break the bypass path like this. So this will give us a 5 stages pipeline with an interval of 1T. And on top of this design, we found there's actually a design space at the graph level. So basically, we can merge the adjacent pipeline stages into one to trade off between the throughput and resource. Like here, we are saving some memory resources and also open more opportunities to do the resource sharing, right? But meanwhile, we can only achieve an interval of 2T. So in ScaleHLS, we introduce a parameter called migran to tune the minimum granularity of the coarse-grained pipeline to enable the graph level throughput and error rate trade-off. So this is the graph level optimization. And we also have loop and directive optimizations, and also some other simplification passes to further simplify the IR. So here I will not introduce all of these passes in detail, but just go through an example to show you how these optimization passes work. So here is SYRK kernel written in C. And this C program will be parsed into ScaleHLS and be optimized at the loop and directive level in MLIR. So the first optimization will be loop perfectization. So similar to the JEMM example we used before, this instruction in between the J loop and K loop is moved to the innermost loop body. And also, similar to the JEMM kernel, this K loop is interchanged to the outermost loop level automatically. So basically, we are detecting the pattern of the loops and find a best loop order for the kernel. And meanwhile, we're also applying loop unrolling to the K loop with a factor of 2 to improve the parallelism of the nested loop. And also, we can observe in the original design, the upper bound of J loop is a variable. So in ScaleHLS, we are also providing a remove variable bound path to try to remove the variable loop bounds to enable to open the opportunity of more optimizations. So here, the upper bound of J loop is substituted with a constant 32, and meanwhile we insert an if statement to conditionally execute the whole loop body. So this is the loop optimizations. After this several representative loop optimization, we are also applying some directive optimization, like inserting the loop pipeline and apply array partition. So here, because we unroll the K loop, there's two simultaneous array access to array A at the address of K and K plus 1. So our array partition path will automatically analyze the IR and find a suitable array partition strategy and factor for each array. For example, in this case, it applies a cyclic array partition with a factor of 2 to array A. Apart from loop and directive optimization, we also provide some simplification paths to simplify the redundant if statement, memory access operations, to simplify the IR. And I want to note that all of these loop, directive, and simplification paths can be applied automatically, and each parameter of an optimization can be considered as a tunable knob in the design space exploration. So to enable the automated DSE, we package all of these transform paths together with an HLS quality of result estimator to a transform and analysis library. So then I will introduce our design space exploration engine. So basically, through profiling, the dark blue points is the Pareto design points in the throughput and area design space. If we map them back to the original design space and use a PCA to visualize the the design space, we actually find those Pareto points tend to cluster together and located at the corner of the design space, which means the variance of Pareto points is much smaller than the overall variance of the whole design space. So on top of this observation, we develop a DSE algorithm. Right. So in the first step, we will sample the whole design space and evaluate each sample design point with the quality of result estimator. And we will extract the Pareto frontier in the evaluated design points, basically the orange points here. And then we will randomly pick one Pareto point and evaluate its closest neighbor. So this is because the Pareto points tend to cluster together. So there's a high possibility that the neighbor of a Pareto point is also a Pareto point. In this case, we are evaluating this blue point. And if this new point evaluated is a Pareto point, then we will add it to the set of Pareto frontier. And meanwhile, if another point like this one is dominated by the new Pareto point, we will remove it from the Pareto frontier. So you can imagine if we repeat the step 2 and step 3, we will update the discovered Pareto frontier and make it better and better and closer, to the real frontier. And finally, we will stop the exploration when there's no eligible neighbor can be found or meeting the early termination criteria. So this will provide us an estimated Pareto frontier in the end of exploration. So I want to note that given the transform and analysis library provided by ScaleHLS, actually the DSE engine can be extended to support other optimization algorithms in the future. All right, then let's take a look at some results of the DSE engine. So we picked 6 computation kernel from the Polybench benchmark and pass them to the design space exploration. So all the problem sizes are set to 4096. So you can find after DSE, among all of these 6 benchmarks, we achieve speed up ranging from 40x to more than 700x. So this speed up is comparing to the original C program, C code in Polybench without the optimization of design space exploration. And we also listed the optimization parameters selected by the DSE engine, including the loop perfectization, remove variable bound, the loop permutation map, and the tiling sizes, pipeline II, and array partition for each array. So all of these parameters are automatically selected by the DSE. And to understand the performance of our DSE under different problem sizes, we scaled those 6 computation kernels from 32 to 4096. So you can observe the performance achieved by our DSE engine is reasonable for all the problem sizes. And then to evaluate the performance of our framework on large and complicated HLS designs, we picked 3 DM models written in PyTorch. So basically, this PyTorch model will be parsed into ScaleHLS and generate synthesizable C or C++ code. So the speed up here is comparing the design that go through our multi-level optimization, including the graph, loop, and directive optimization, and the designs just go through the ScaleHLS compilation flow, but without the multi-level optimization. So we also did an application study to understand the contribution of the directive optimization, loop and graph optimization. So you can observe actually the D, L, and G here represent the directive, loop, and graph optimization. So we can observe all the 3 levels of optimization contributing to the speed up here. All right. Then conclusion. So first, we present ScaleHLS, an HLS-based HLS compilation flow, MLIR-based HLS compilation flow, features a multi-level representation and optimization of HLS designs, and support a transform and analysis library dedicated for HLS. We also enable an end-to-end compilation pipeline by providing a safe front-end and a C++ backend. And we develop an automated and extensible DSE engine to search for the Pareto frontier in the design space. And finally, experimental results shows the strong scalability of our framework, and also we achieve a significant performance and productivity improvement. So the ScaleHLS framework has been open sourced on GitHub, and also we have archive paper published where you can find more details of the project. And finally, several future directions, including IP integration. For example, at the graph level, we can integrate existing IPs to the program, and also other DSE algorithms and the machine learning based quality result estimation, and also maybe we can directly generate RTL code within MLIR to further improve the performance we can achieve. And that's all for today. If you have any further questions, please feel free to contact me at this email address.
Thank you very much, Han-Chen. I'd like to thank everybody for attending, and thanks to the two speakers for two great talks. A reminder to any researchers, you're very welcome to apply to join our XACC program and get access to the Alveo Compute acceleration hardware. With that, I'll close this session for now. Thank you very much.